In this segment, we'll take an example to see that how many significant digits can we trust in our solution. So let's suppose somebody gives you a set of equations like this: 1, 2, 2, 3.999 xy is equal to 2, 4. And somebody says, hey, I'm going to find the solution here for this set of equations. Can you tell me how much I can trust the solution? So what I'm going to do is I'm going to say, hey, this is of the form ax equal to c. Can I find the norm of a? So the row sum norm of a will be 5.999, because the absolute value of 1 plus absolute value of 2 is 3, absolute value of 2 plus absolute value of 3.999 is 5.999, so we get norm of a to be 5.999. Now I can also calculate the inverse of the matrix. So I can calculate the inverse of this matrix, and that turns out to be minus 3999, 2000, 2000, and minus 1000. So that's what A inverse turns out to be. So in this case, the norm of A inverse, the row sum norm, turns out to be 5999. So that is the row sum norm of A. That's the row sum of A inverse. And what I'm going to do is I'm going to calculate my condition number. So the condition number of A will be norm of A times norm of A inverse, and I get 5.999 times 5999, and this number here turns out to be 35990. So that is the condition number of A. And then what I'm going to do is I'm going to take the condition number of A and I'm going to multiply it by the machine epsilon. So let's talk about the IEEE 754 standards for single precision. The machine epsilon for that is 0.119 times 10 to the power minus 6. So this is the machine epsilon for a single precision number, 0.119 10 to the power minus 6, and this one gives me 0.4290 times 10 to the power minus 2. And now what I want to be able to see is that, hey, what is that largest value of m? So I get 0.4290 times 10 to the power minus 2, and I need to say, hey, what is the largest value of m for which this number here turns out to be less than or equal to that number. And if you do the calculations, you will get m is equal to 2, or m is less than or equal to 2. That's what you're going to get as the answer, which means that you cannot trust more than 2 significant digits in your answer. So this is the number of significant digits which you can trust in your solution based on the condition number, knowing what the machine epsilon is, and comparing it to this number right here. If we were doing the problem in double precision, this number would be different. It will be much smaller than this number right here, and so eventually you will find out that you will be able to trust more significant digits if you are doing double precision. If you're doing quad precision, you will be able to trust even more digits. So it is a combination of the machine epsilon and the condition number which is going to tell you whether your system equation is well conditioned or ill conditioned. And that's the end of this segment.